Welcome to an example on how to use the divergence theorem to evaluate a flux integral using spherical coordinates. So we want to calculate the flux integral, often expressed in this form here as well, where the vector field F is given and the surface S is the surface of the solid bounded by the hemispheres given by z equals the square root of the quantity 4 minus x squared minus y squared, z equals the square root of the quantity 1 minus x squared minus y squared, and the plane z equals 0. So let's first take a look at this graphically. The surface S is the surface that bounds the solid between these two hemispheres above the xy plane graphed here in yellow. And I've also graphed the vector field F in purple. So the value of the flux integral is equal to the net flow or total flow across the surface, again, that bounds the solid between these two hemispheres and above the xy plane. Before we set this up, let's review the divergence theorem. The divergence theorem states that the total divergence of a vector field in a solid region V equals the total flow across the boundary surface S. So V must be a solid region bounded by the surface S, oriented by a unit normal vector directed outward, and the partial derivatives of the vector field F must be continuous over the solid region V. So we can evaluate the flux integral shown here on the left by writing it as a triplet integral over the solid region V of the divergence of the vector field F differential V, which can also be expressed in this form here. So this shows a relationship between a triplet integral over a solid region and a surface integral over a surface. So going back to our example, using the formula here on the far right, let's first find these partial derivatives, where P is equal to 4x cubed z, Q is equal to 4y cubed z, and R equals 3z to the fourth. So the partial of P with respect to x equals a derivative of 4x to the third z with respect to x, which would be 12x squared z. The partial of Q with respect to y equals the derivative of 4y cubed z with respect to y, which would be 12y squared z. And the partial of r with respect to z equals the derivative of 3z to the fourth with respect to z, which would be 12z to the third. Which means the given flux integral often expressed in this form here as well, the double integral over the surface S of f dot n differential S, where this differential S represents a small change in vector area, and this differential S represents a small change in surface area. So applying the divergence theorem, this is equal to the triple integral over the solid V of the sum of these partial derivatives, which we already found here. So we have 12x squared z plus 12y squared z plus 12z cubed differential V. And now from here, because the solid region V is bounded by two hemispheres, we'll use spherical coordinates to evaluate this triple integral. Where for a quick review, in spherical coordinates x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. And x squared plus y squared plus z squared equals rho squared. So looking at this integrand function here, notice how if we factored out 12z, we'd have 12z times the quantity x squared plus y squared plus z squared, which means in spherical coordinates we would have the triple integral. We'll come back to the limits of integration of 12z, again where z equals rho cosine phi. So we have 12 rho cosine phi. And then x squared plus y squared plus z squared equals rho squared. And then for spherical coordinates, remember differential v is equal to rho squared sine phi d rho d phi d theta. And now let's work on determining the limits of integration for rho, phi, and theta. Remember, in spherical coordinates, rho is the distance between the point and the origin. Theta is the angle counterclockwise from the pole or positive x-axis in the xy plane, and phi is the angle between the positive z-axis and the point. All that information is shown here. So limits of integration for rho would be from 1 to 2, because the radius of the inner hemisphere is 1, the radius of the outer hemisphere is 2, and then for phi, remember that's the angle down from the positive z-axis, and because we're only concerned about the solid above the xy plane, rho would be from 0 to pi over 2. And then theta would be from 0 to 2 pi all the way around the circle in the xy plane. So from the positive x-axis all the way around the circle. Now let's work on evaluating this on the next slide. Let's go ahead and factor out the 12. So we have 12 times the triple integral. Then we have rho times rho squared, that's 4 to the 5th. Cosine phi sine phi, d rho d phi d theta. So we first integrate with respect to rho, treating phi as a constant. So we'd have rho to the 6th divided by 6 times cosine phi sine phi, or 1/6 rho to the 6th cosine phi sine phi. Let's go ahead and factor out the 1/6 and then perform substitution for rho. So 12 times 1/6 would be 2. And then we'd have 2 to the 6th cosine phi sine phi minus 1 to the 6th cosine phi sine phi. So here we have 64 cosine phi sine phi minus 1 cosine phi sine phi, which would be 63 cosine phi sine phi. If we factor out the 63, 2 times 63 equals 126. So we have 126 times the double integral of cosine phi sine phi d phi d theta. Integrating with respect to phi, we'll perform u substitution, where let's let u be equal to sine phi, and therefore differential u equals cosine phi d phi. So all of this we can think of as just u du. So in terms of u, the antiderivative would be 1/2 u squared, which means in terms of phi we'd have 1/2 sine squared phi. Let's go ahead and factor out the 1/2. 126 times 1/2 is 63. So we'd have sine squared pi over 2 minus sine squared 0. Sine pi over 2 is 1, 1 squared is 1, sine 0 is 0, so sine squared 0 would be 0. So we end up with just 63 times the integral from 0 to 2 pi d theta, if we want 1 d theta. Integrating with respect to theta, we have 63, and we have theta. Let's finish this on the next slide. So we just have 63 times the quantity 2 pi minus 0. So the exact value of the flux integral is 126 pi, which is a decimal approximation, is approximately 395.8407. So going back to our graph one last time, we just found the total flow across the boundary of the surface S, which bounds the solid between these two hemispheres above the xy plane, is 126 pi, which based upon the divergence theorem is also the total divergence of the vector field in the solid region V. I hope you found this helpful.